Okay, so here's a few words for the next homework. It will be due, no due date, by the way. It will be due the Monday, so I'll give you an extra weekend because I want to get a little bit further into the material here. So the first problem is, this is kind of a classic. Some of you, algebra course, your number theory course, may have done a problem like this before. Let D be a square-free integer. That means it's not divisible by any integer, any square of an integer except for one. We define a quadratic ring of integers to be R joined with Z omega, which is the set of all Z linear combinations of 1 and omega. Where omega, what is omega? It's this thing. It's the square root of D in the case that D is equivalent to 2 or 3 minus 4. And it's 1 plus radical D over 2 is equivalent to 1 minus 4. We define the norm map from R to Z by the norm is this. Multiplies garbage out. Where omega bar is basically it's the conjugate of this. Verify these properties of the norm. Let me give you a little hint on this problem. This is obnoxious as anything, right? But really what this is, when you multiply two things out like this, you get a mass, right? And so basically you have to multiply these four polynomials. Notice that when you input A plus B omega, you just get A plus B omega here, and you get A plus B omega bar here, right? Prove that the correspondence from A plus B omega to A plus B omega bar is an automorphism of that ring. So basically what this does, the norm is it takes this element itself, which is the identity automorphism, and this thing, which is another automorphism. If you prove that this is an automorphism as well, it makes a lot of this easier. And you will thank me because it will save you some computation. But show the following properties of the norm. The norm of the product is the product of the norms. The norm is 0 if and only if the element that you plug in is 0. You will need the square root for that, by the way. X is a unit in R if and only if its norm is plus or minus 1. Number C, use the norm map to show that Z adjoined with the square root of negative 14 is not an HFD. I haven't told you what that is, but that's, we'll get to that today. That's an integral domain. It's atomic. Any two factorizations have the same length. So in other words, in part D, show that you get some elements that factorization length. And use the norm map to show that this thing is not a UFD. Number 2, let R be commuted with identity. You say that R is von Neumann regular. If for all A and R, there's an X and R, so it's A squared X equals A. Let R be von Neumann regular and P a prime ideal. Show that R mod P is the same thing as R localized. You don't know what R localized is yet, but we'll get to that in localization maybe today. What? Number 3, let R be a principal ideal domain, of course, it's okay. Show that if you have two elements A and B, not both 0, then the greatest common divisor exists and is a linear combination of A and B. This is an important property of the integers that any two elements have the greatest common divisor, and that greatest common divisor is a linear combination of two elements in question. And number B, show that any overring, and what I mean by that is a ring that lives between R and T is in fact a localization. There's that word again. Number 2. That is basically showing the ring between R and its quotient field can be obtained by taking one set of element denominators. Use this to conclude that any overring principal ideal domain is principal ideal. And 4, give an example of a commuted ring with identity with elements X and Y, such that X and Y are associates by the definition that I first gave you. That is to say, X divides Y and Y divides X. But there's no unit such that X equals Y are. My hint to you there, to satisfy the definition, is you need to look at something that's got 0 values. Okay, this will be due a week from Monday. And this is, hooray, hooray, the second to the last one, except for doing that. Okay, any questions? So, the last thing that we talked about was this business about and this, of course, this operates under the blanket assumption that R is minimal domain, because one of the directions is not true if R is not a domain. Let me give you a really, so this is a classic. Like I said, many of you may have seen this before in other algebra classes, and I promise you, you've seen it before. Much more on with this one. Correlate 5, 4, 16. Yeah, I love this. It's very slick. For the PID, I want to use this characterization here, so I need to show that every non-zero prime ideal is non-zero prime element. Since R is a PID, this prime ideal P is generated by an element little p, and there you go. Any non-zero prime ideal contains a non-zero prime element. In fact, that's been generated by prime element. You're done. That's the I really, that's art right there. Okay. Let me generalize another property that the integers have. One of the most powerful things the integer's got is it's got the Euclidean algorithm, right? You can divide and get a remainder. So we're going to make a definition here. Let domain. Let R. There are many definitions about this, and I'll make a remark about this. We said that R is a Euclidean domain. Actually, the discrete code set such that all phi of AB to be bigger than phi of A for all AB and R not 0. And 2. If two elements are, or B is not zero, I can divide A by B. And leave the remainder off. So what I've done here is I've divided A by B, the quotient Q, remainder R. The Q, R, and R equals zero, or Q of R is strictly less than P. That's what I divided. And so Euclidean algorithm, basically what it means is this B generalizes what we use in the integers, which is the absolute value function. It's a function that puts out natural numbers zero. And if I divide A by B, I can get a remainder. It's either zero, which means B divides A completely, or a remainder in some sense is smaller than what I divided by. This allows an algorithm where I can get smaller and smaller remainders cascade down. By the way, it can be shown, it's difficult. If you see some versions of Euclidean, they do not make this requirement. And it turns out that if you have any Euclidean domain that has a Euclidean function that say it doesn't satisfy this, you can actually massage your Euclidean function and force it to satisfy this, right? But I believe you need choice to do that actually. And if you have this one, it allows you to prove some of it as well. But so one is sort of an option on that. Okay. Here's some examples. That's the one you're used to. The Gaussian integers is also Euclidean. Anybody know what the Euclidean function is? Yeah, it's the norm function. You can use the norm function. Here's another. I want to talk more about polynomials and power theory later. I'm going to rely from now on sort of intuitive knowledge. So that's the field. Here's the way the function works. Anybody want to guess this? Let's see. What is it? This example will makes you realize perhaps a couple of things. Number one, this is why we want the Euclidean function to operate on non-zero elements, because polynomials, the degree of the zero polynomial is undefined. So you want that going on. This example right here is one of a couple of reasons why partial fractions work. How many of you remember doing partial fractions in calculus? How many of you enjoy torturing your undergraduate students doing it now, right? Well, here's the reason that works. I mean, if you take something like so you might want to understand the way this function behaves if you're in calculus. And so what can you do? You can divide this in here. Let's see, this goes in x squared terms, but it's x squared plus x cubed plus 5x squared. I subtract, well, it doesn't work up very well, but it makes 4. And I subtract here, bang, bang. Now, this goes in negative x times. Minus x cubed minus x squared minus 5x. And it starts making sounds again. Bang. Minus 4x squared. Plus 5x 1. Right? And now it goes in again, negative 4 times. Right? Minus 20. And if you subtract this off again, I get 9x plus 21, I guess. Okay. And so what that means is, and we've all kind of done this before, is this thing is this quotient of what I divided by plus here's my remainder here, 9x. And notice this doesn't go in anymore because the x squared, the 9x is too small. And that's what the Euclidean algorithm for this particular ring is measuring, right? The degree. Here the degree is 1, which is strictly less than what I divided by. So I'm done. Right? And that, by the way, this allows me what I've written here is right. What that means is that this thing is so let me write it up here correctly. This means x4 plus 1 is equal to remainder. What I thought about plus of course this is easy to verify, multiply this out, fix them, get it. It also means that this quotient, if you want to consider the fractional function, if you divide by x squared plus x plus 5, that means the quotient looks like this quadratic polynomial plus this fraction that actually goes to 0 as x goes to plus minus infinity. So figure things out that way. We'll talk maybe a little bit more about this later. Now let's look at formal power series. Right. Now here, I probably shouldn't say this before, but the analysts are the ones who mess this up by trying to plug things in, right? We're algebraists. We don't plug anything in. It's just treat it like a giant polynomial, multiply things out. What does a typical element look like here? A typical element, if I wrote it in its most general form, right? Now let me point out that some of these beginning terms might be 0, so I could write it this way. Right? So in general, I can write an arbitrary power series this way. X to some power n times this, where an is non-zero. Notice that I can write any non-zero power series in this form. And my Euclidean algorithm on this, my Euclidean function, I should say. So it's sort of the opposite of degree that we have polynomials. Instead of looking at the highest power, which you always have polynomials, you sort of look at the lowest power. Okay. another definition. Obviously, need for definition, 5422, 5420. I would say every non-zero, non-unit factor in the items where we say that R and HFD yeah. Given irreducible, they have to be J, then A1, A2, AN, B1, BM, implies in so let me give you some examples and non-examples of this. So what an HFD is it's just something that you can factor everything into irreducibles, and you may not have any factorization, but what you do have is every time you can factor, whenever you can factor an element, say in the irreducible in two different ways, and the links have to be the same. So let me start there. I mean, certainly anything that has unique factorization gets halfway there. Well, let me give you some better examples. Let me give a example factorization. Now, this is incomplete for a lot of reasons. Number one, I haven't proved that any of these things are reducible, but they are. In this particular ring, 2, 3, and each of them. And I certainly haven't proved, even though it works just for this one, I haven't proved it works for every one, but it does. You need actually some algebraic number theory to know why this works. Also, and what I mean by this notation here is these are all powers here, coefficients in K, but I demand the constant term being smaller than F. These are all polynomials with coefficients in K, but I demand that. So, for example, K could be reals and F could be rationals, and this could be all real polynomials, but I demand the constant term be rational. These are HFDs and or UFDs, if and only if they are the same. So in other words, these are usually not UFDs. Let me give you a non-example. HFDs are actually a pretty rare class. And if you just walk up to some ring on the street, then, well, first of all, it's probably not an atomic, but it's probably not an HFD. you have a field. This one's easy to see about an HFD, and we've actually sort of done this example. X6. We've already mentioned the fact that X cubed and X squared are irreducibles in this particular domain, and it's not an HFD because I put up there a factorization of like 3 in the irreducibles and a factorization.
So that's not a UFD and also not.
I'm sorry.
So it's not both, or it's just not a UFD.
Oh, right here.
This is.
Oh, yeah, yeah. So if you're a UFD, you're an HFD, right? If you're an HFD, you're not necessarily a UFD, and if you're not an HFD, you can't be. So, yeah, this doesn't have to need factorization or even half, the half factor. Definition of factorization flavor. I'm going to say here. Element D is said to be a greatest common divisor set S. And if you like, you can assume this is not. Divisor. Set S. Yeah. Well, it's got to be a common divisor in the sense that D divides S, for all S and S. So that's a common divisor part. And the greatest is if C divides S, for all S and S. And C divides C. Okay, so this is what I mean. This generalizes the notion of greatest common divisor of anything. Of course, I didn't even say the set had to be finite here. So what does it mean to be a greatest common divisor per set? It means that it's a magic element D that divides everything in S. And if you can find something else that divides everything in S, then it has to divide the greatest. I do not claim that for an arbitrary set, the greatest common divisor exists. Right? In some domains, yes, these things exist. In some domains, they don't. Some rings even. Here. So here's the theorem concerning this. Let R R is a PIR. Remember what we reminded what that is, the principal ideal of the ring. It's not necessarily minded here, right? How is it necessarily minimal domain? Whatever you have is principal. And that if you have a set of, say, n elements, then DFDs exist. Exist. And is a linear combination. Let it say G, this D doesn't exist, then R1, A1. UFD, and let me add some hints to play with this theorem here. Why is A true? I'll sketch out B. Well, for A, consider the ideal generated by A1 up to AN. Right? That's an ideal. And this is F R is inference ideal. Note B divides AI to all I. Because each of these AIs is in the ideal generated by D. So D divides it. Well, also, D is equal to R1 A1 plus R2 A2 R1 A. Because these two ideals are the same. That means that D is in here, so let's go into a combination of the A's. And finally, how about the greatest? Suppose C divides AI for all I, then C divides D. This equation makes it pretty obvious that if C divides it to D, then it divides it. For the second one, just for ease, I will assume in part B, I'll assume that none of these are zero. Because actually, if every element is zero, then you can show the greatest common divisor is zero, or you can just throw out that as well. And if some of these are zero, you can throw out those, right? It's like for example, A1, 0, 0, comma H of A, and the greatest common divisor of that. So, anybody want to guess what is the how we do it? Actually, let me start you off with some color. Now, you might criticize me if say, well, Jim had to double check the same times. And in fact, but, right, because if, for example, if I'm P1 is in A1, then I'll just have this 0. Right, okay. And of course, this also takes care of 1, because 1 factor has P1 0 at the end. Anybody guess what the GCD? I'll guess it is. I feel like I'm not observation. Only have to put numbers on. Just take the small things. By the way, anybody want to guess what would happen if we took the max of those two? What you would get? Get the least common multiple. That's acceptable. So that's essentially why it works. I just did it for 2, but you can proceed on this by induction. Let me also point out that I didn't say that in the UFD that the greatest common divisor is a linear combination. And that's because it's not true. So if you look at a polynomial ring over a field of 2 variables, that is the UFD. I'm going to prove that later. I'm going to prove the theorem that that's a constant. X and Y are prime. Let me give you a quick proof of that. If you take this polynomial ring into variables and you mod out by the ideal generated by Y, basically that kills everything in Y, and you're left with a polynomial ring only in X, which is the neutral domain. Same thing with modding out by X, you get Fy, and so since you mod out, you get an integral domain, X and Y are both prime. And of course, X doesn't divide Y and Y doesn't divide X, because neither X over Y nor Y over X is a polynomial. So GCD of X and Y is actually 1. It's X to the 0 times Y. But you cannot find polynomials in 2 variables, P1 and P2, such that multiplying X by P1 and Y by P2 equals 1. And let me give you a proof. If you plug in X and Y equals 0 to the right side, you get 0, and if you plug it in the right side, you get 1. So getting 1 is a linear combination. This is impossible, and so you cannot expect for any UFD for the greatest common divisor to be a linear combination of the elements. Okay. Number definition. Again, click on the domain. Non-zero elements. Finite set, non-zero element, has a very common divisor symmetrical domain where every two pair of non-zero elements is greater than 25, we call that a GCD. For example, any principal ideal domain, any UFD is GCD domain. If R is a GCD domain, and any given AD or 0 GCD AD 1A or 2B, that is to say GCD actually is a linear combination, then R is a grade 2. And there's a bunch of strange accents on this letter. Equivalently, every finite generated ideal what it needs to be a basic domain is GCD domain where every given any two elements, GCD is actually a linear combination. This is equivalent, so you might sort of satisfy yourself on this a little bit. This is equivalent to saying that every finitely generated ideal is exactly is a principal ideal. And I'll leave you with a challenge. Let me point out also that any principal ideal domain is basic domain. The converse is true. See if you can think of anything of a basic domain that's not principal. That is, every finitely generated ideal is principal, but not every ideal is finitely generated. Okay. Any questions? So, localization is many things. It's a way to construct a new ring from an old ring. It's a technique. It's important in algebraic geometry, muted algebra, all over the place. Basically, you all know how to add fractions, right? Been doing that since we teaching you how to do that in grade school. Given a ring Z, given, for example, Z, it's got torsion to it, right? And this is every fraction for the denominator is not zero. And there are, of course, other rings. Anybody name me a ring street here? Any ring bigger than Z, but less than. How about this? This is the smallest ring. It contains all of Z plus 1/2. So a vertical element of this is notice that when you add any two elements like that, so that when you multiply it out, it's bigger and bigger, it's still like that. And here's another example. Now it's going to take later. The ring of all rational numbers where the denominator is odd. Notice the denominator could be one certainly odd, so this contains all the integers, right? But it's got other stuff. Essentially, it's got 1/3. So, let me point out that notice that if B are odd, and so is B. So when I add up two things to the non-denominator, I can write the fraction as the non-denominator. Great. And the same is true for multiplication. If B and B are odd, so B comes. Notice that what I've done is I've taken the ordinary integers, my old friend, and now I have allowed fractions to come out of the set of odd numbers, right? And what do I know about odd numbers? That is a multiplicatively closed set. If by an odd and I multiply, it's an odd. And you see that was important when I tried to add and multiply the fractions, because I wanted odd denominators to give rise to odd denominators, right? This is sort of the antithesis of this. Another way I can write this is the set of M. Why is that? Because what I can do is I can just collect the denominators, right? For example, notice that the largest power of 2 in the expression here is 2 to the m. So I can calculate this over 2 to the m. Notice that this one has got sort of a similar flavor. I've taken my old friend, the integers, and now I've just allowed a set of denominators. And here, instead of being odd, it's only exclusively the powers of 2. And so this is the idea behind localization. What you do is, so let me paint how the yellow brick road is going to work. I want to do this more general in domains, but since I'm kind of painting the roadmap for you, I'll specialize in the I can make this new ring RS. Here's my suggested notation. So what I'm doing is I'm making fractions. And I do the rules of addition and multiplication the way it used to. And this is called the localization of the ring R set S. So what I'm doing is I'm taking some subset and allowing denominators. Notice that I want to probably avoid having 0 in this set because we all know that we get the problem to denominator. Let me point out that in this case only, R is a subset, but can be construed as a subset of RS because you can take S to be, for example, 1 and bring that 1. So you can think of R as sort of sitting inside of it. Now, one of the questions you should ask yourself is, in the more general case, what happens if you have 0 values? For example, what happens if S1 times S2 is 0? What will go on there? You need to avoid this kind of thing. You need to talk about localizations more next time. Any questions? Yes.
Did you say that that was the localization of R on S?
At.
At S?
Yeah, they usually say at.
The localization of R at S?
Yes. Other questions? Questions out there? All right. Well, let me recommend the math club today. Wayne Goddard, if you haven't heard him talk, he's always an interesting fellow. He's going to talk about dot land. That should be a kind of fun way to segue into the weekend. It should be a bloodbath since Connecticut's coming up here. We'll see how that works out for us. Y'all have a good one. We'll see you on Monday.